So we are going to examine what it looks like to take the derivative of an inverse function. Before we do that, let's first jump in and take a look at what an inverse function is or isn't when one might or might not exist. So I have two functions to compare. One is x cubed plus x minus 1. That roughly speaking looks like this graphically, whereas y equals x cubed minus x plus 1 sort of looks like this. And we say that this function has an inverse while this function doesn't, because this function is something that we call one-to-one. In other words, every output on this function corresponds to a single unique input. Whereas here, this output at y equals 1 actually corresponds to 3 different input values. There are 3 different x values that allow this function to be x equals 1. If you were to think about what this would look like graphically, when you think about an inverse function, an inverse is reflected graphically across the line y equals x. So here, if we draw that y equals x line through here, our inverse function would look kind of, let's see if we can get this going, something like that. Whereas if I reflect this across the line y equals x, the resulting inverse is going to kind of snake through here and be here and then sort of do one of these things. And the same way this wasn't one-to-one across the line y equals 1, now this inverse is going to have different spots that don't make the inverse a function. So we say that this doesn't have a true inverse. Let's take a look at a function like this that does have an inverse and see if we can find what the derivative might look like for that function. So where people like to start is they say, well, let's just find what the inverse would be, right? Which we denote as f inverse of x. Let's see what the inverse would be, and then we can take the derivative. Well, if I consider y equals x cubed plus x minus 1, everybody always remembers that x equals y cubed plus y minus 1, and then I got to solve for y. Right, I get y by itself, and if I can do that, I'll have an inverse function. Go ahead, take your time, and see if you can get y by itself here. It's going to be really challenging to do that. You're going to add 1, then maybe divide a y out, and you're just going to work yourself in a big circle of logic here, where you're not going to be able to get y by itself. So instead, if we can't get to what the inverse is algebraically, but we know like there is one that exists here, and we want to talk about the derivative, we need to kind of attack this in another way. So first, I want to consider what happens on an inverse function to the derivative as we switch inputs and outputs. We know that on f of x, the input or the point 2, 9 exists. If we went over 2 up 9, that would be a point that's on this curve. That means that on the inverse, we have the point 9, 2. Because remember, that's what makes this reflection across y equals x occur. We switch inputs and outputs. The input on f became the output on f inverse, and the output became the input. And we're going to use this to our advantage. The second piece that we can think about here to sort of use this to our advantage is if we know that the slope of the tangent line sort of looks one way on f, and we're reflecting that across the line y equals x, we actually end up with a reciprocal slope relationship between f and f inverse. In other words, if on f of x, f prime was equal to, say, I don't know, 10, maybe it's a really steep tangent line, on f inverse, we have an f prime equal to 1/10. But it's equal to 1/10 on like the flipped input output. So the 2, 9, the 9, 2 version of the 2, 9 flips the 10 to the 1/10. And that sort of, just based on this graph, sort of makes sense to me as we have a really steep tangent line here and then a positively sloped but sort of shallow or less steep tangent line here. So how can we really apply that relationship and figure that out? Well, I like to use the formula. The derivative of the inverse at some value a equals 1 over the derivative of the inverse at that a value. So it sounds kind of the same. The derivative of the inverse is equal to 1 over the derivative of the inverse, but they're actually written differently. This is in the formula written like a composition of functions, whereas this is talking about the derivative of the function f inverse. In this case, right, or in all cases, a is going to be an input on the inverse. So here I want to find, maybe using this f of x, I want to find f inverse of 9, the derivative of the inverse at 9. Well, that's equal to 1 over the derivative of the inverse at 9. So the first thing I need to do is evaluate the inverse at 9. Well, since I know 9 is an input.
Students, if you have not already, display for your students the run, hide, fight, and say something training video. Please do that at this time. Thanks so much and have a great evening.
So the first thing I'm going to do here is find the inverse at 9. The inverse at 9 has an output of 2 because of the 2-9 relationship back on f. So this is equal to 1 over the derivative at 2. And to finish this out, I just need to know the derivative at 2. Well, I know what f was, so f prime of x, just using a power rule, is 3x squared plus 1. So f prime of 2 would be, let's see, 4 times 3 plus 1, 13. So I end up with the derivative of the inverse at 9 being 1 over 13. And look at this relationship. Just like we kind of guessed before, we sort of approximated at 10 and 1/10. The derivative at 2 on f is actually 13. That's tangent line slope is 13. Whereas if I flip the point and go to the point 9, 2, my tangent line slope is just the reciprocal of that, 1/13. So I'm able to use this formula to sort of make that reciprocal relationship sort of more efficient for my use in a problem to find the slope of the tangent line or the derivative of an inverse function at a particular value.